Okay, so we're on 6.3. We are going to look at determining sample size, the minimum sample size needed, like we did on a z-interval for a mean, like how many people would I have to sample to estimate the true average height of JSerra students within an inch. We're going to do the same thing, but very much like you see on the news polls. You might see that candidate A has 48% of the vote, plus or minus 1%. Well, what if I wanted that within plus or minus 0.5%? How many people would I have to sample? So that's what we're going to answer, but I want to do a quick little review problem first, so hopefully we're all on page here. So suppose we randomly sample 92 students and find that 22 of them have pet cats. I know you guys are liking this example, right, Meow? All right, so I got some response out of that. Oops, what did I do? I hit the wrong button. All right, I hit the wrong button again. Close that. All right, so to start out, before we even construct a confidence interval here, just want to check the conditions to make sure that we can actually use our procedures here. And we're doing two conditions, random and the normal condition. So we need to check, first of all, theoretically, was this random? Well, it says random, right? So, yeah, sample was random, it says. That was given. You guys remember what the normal condition was for this? So just a heads up, we had seen in a z-interval for a mean or a t-interval for a mean, the conditions were either that the sample size was over 30 or the population is a normal distribution, or if the plot of the data reveals no strong skewedness. Well, how is this different? This is different. What we did in 9.1 and 9.2 were means. Again, think about the question you were asking people. How tall are you? That's a numerical data, right? Now we're asking, do you have a pet cat or not? This is categorical. It's either going to be a yes or a no. And the answer is yes. Just kidding. So there's a different normal condition. Do you guys remember what those normal condition was for this chapter?
NP and NQ.
Good. Have to be greater than 5. Again, this is very common for students to get these two mixed up. But in this case, I need to check that NP, and in this case NP hat, are greater than 5, and NQ hat are greater than 5. And again, why am I putting hats on them? Because I don't actually know the true percentage of people who own cats. Again, the variable P by itself would be the true proportion of all students who own a cat. A P hat, in this case, represents the sample. We sampled 92 people, for instance. So to check this, and really NP hat and NQ hat end up being the number of successes and the number of failures. And I think you guys saw that on my last video, right? So two ways. You could calculate NP and NQ hat, or just talk about the number of successes and the number of failures. So in this case, I'll just change up color here. There were 22 successes, and if you don't believe me, you can multiply N. N again was our sample size was 92. P hat is technically 22 over 92. So you can see those denominators would cancel out, and I'll be just left with 22. Q hat in this case is going to be the number of failures. You could calculate the number, or let's see, there's going to be 70 out of 92 people who in this case didn't own a cat. So again, NQ hat would be 92 would be N, and there were 70 people who didn't have a cat over 92. You could see I'm just left with 70. This is my number of failures, so both values are greater than 5, which allows us to use a normal distribution. So construct a 95% confidence interval. To remind you guys, the formula for proportion is P hat plus or minus the critical value of Z times P hat Q hat over N. And at this point, it is kind of nicer, maybe on the side, to get some decimals for each number. So P hat was our 22 over 92 students who had a cat. To me, that's not enough. So 22 divided by 92, I got We got 0.2391. Let's kind of go to 4 decimal places. You could think of this as 23.91%. So Q hat then is going to be 1 minus P hat, so 1 minus 23.91, which is 0.7609. So putting this all together into my original formula, I have P hat was 0.2391. Critical value of Z at a 95% confidence level. Anyone? Get off the table. Alright, I'm just speeding things along here. It's 1.96. So this will be now times P hat 0.2391 times Q hat 0.7609. And I'm sorry, the stylus, it's really hard for me to write neatly with this, all over our sample size of 92. So I'm just going to put in that margin of error in my calculator. And I got a margin of error of 0.0871. So I'm essentially saying, hey, the true percentage of students at this school or wherever this sample was taken is 23.91% plus or minus 8.71%. And for the sake of time, I'm just not going to subtract and add the two together for a confidence interval. But I wanted to get to, well, what if I wanted to I really want to get a good estimate of the proportion of students who own a cat. How many people would I have to sample? So again, I apologize if you're taking notes right now in class. This video will be back up online and you can just check it real quick. So to determine minimum sample size, so our margin of error is that thing on the right. That's our Z, critical value of Z, times P hat, times the square root of P hat, Q hat, divided by N. So what if I wanted to solve for N, which is our sample size here? And really what I'm saying too, when I say a minimum sample size, I want this margin of error, and I'm really saying this margin of error. So you give me a number that I put in, and the bell has rung, so we're going to have to fix. Okay, let's restart here. So we want our margin of error, some given margin of error, to be at most this value right here. So what we need to do is we need to solve for N in the denominator, which is our sample size. So step 1, I guess there's a lot of different steps you can do here, but let's divide the other side by our critical value of Z, which is positive, so we don't have to worry about the inequality sign switching. Next step, let's square both sides to get rid of that, that square root. I'm going to go off to the side here. I'm going to multiply N to the other side, so I'll have N E squared over Z. Critical value of Z squared is going to be greater than or equal to P hat Q hat. And lastly, I'll multiply by the reciprocal, and I'm going to get Z, the critical value of Z squared times P hat Q hat all over the margin of error squared. So this here on the right, I'll circle it here. And that's a Z, that funny looking thing, that's ZC. Again, I apologize, I'm not good at writing with these stylists. It's not very natural to me. But this is going to be, let me rewrite it one more time. Yellow's an awful color to choose. I'll write it in dark blue. So this is going to be the formula to use for the sample to determine the minimum sample size. So let's look at this formula for a moment. Z C quantity squared, that's going to be dependent on the confidence level. You should be able to find that. On the denominator, the margin of error is going to be given. Just make sure you write the margin of error as a decimal. So make sure you write that as a decimal. For example, 1% is 0.01, so make sure you can you translate it. But what about p hat and q hat? Don't I need to know p hat and q hat? What values do I use for those? So so let me write this again one more time here. The margin of error again is given, but what do I do for p hat and q hat? Well, there's two different cases. So for p hat and q hat, either use a reasonable estimate, really it should be based on something, based on previous work or previous studies. But better yet, use 50% for both. That is 0.5. And the reason why is this is going to maximize the margin of error. So pretty much what that means is that if I use this 50% for each, I pretty much can't be wrong. I'm guaranteed to have the correct sample size. So let's just see this in action here. So what's the minimum sample size needed to estimate the true proportion of students who have pet cats within plus or minus 2% at a 95% confidence level? So there's my formula again. And since no reasonable estimate is given, you'll see some problems in your homework. They actually tell you to use 48% or use 21%. But let's just imagine I have absolutely no idea how many people have pet cats right now. So I have no reasonable estimates. So we're going to use 0.5 and 0.5 for p hat and q hat. So I'm going to change colors and just do the calculations on the side, then we'll call it a day. So n has to be greater than my z squared, which is 1.96, times 0.5 times 0.5, which I'm using for p hat and q hat. Then be careful on this margin of error because plus or minus 2%, so my margin of error is 0.02, and I'm going to have to square that. So now I'm just going to put this all in my calculator. And if I did everything right, I got, wow, that's a lot of people actually, 2,401 people. You surprised? Is that a lot of people? It is, isn't it? But let's just look back at the previous example when we constructed our confidence interval for using 22 out of 92 people. I had my margin of error at 8%, almost 9%, 8.7%. And that was sampling 92 people. So I don't want to say it makes total sense that we're having to sample this many people, but it makes somewhat of sense. So I hope you enjoyed this lesson, and I'll catch y'all on the flip side.